So up until now, we've been looking at what we call point charges. Charges that are, I've been drawing them as little circles, and they occupy a specific spot, a specific point. We always start there, but point charges are not very convenient because the math gets kind of yucky. Here's the problem. Don't write this down. So if I have a point charge here, let's say it's positive, and I'm moving a negative charge to the right, the problem, maybe I have, I'm a little invisible angel pulling this charge to the right. Now that charge wants to move to the left, which means I'll have to do work, Curtis, to move it to the right. The problem is, as soon as I move, both the electric field and the force are changing. They're changing all the time. So what we would like to do is we would like to find a situation where the electric field, and therefore the force, is constant, isn't changing, because it makes the math much nicer. Otherwise, we have all those equations with the r's in the denominator and long and yucky. So that brings us to this situation. Another important voltage problem is the parallel plates problem. Two metal plates that are parallel to each other, not very far apart, and fairly long, this long or longer. Large flat metal plates are charged up using a power supply, using a plug or battery. Usually one plate is labeled positive because it's at a higher voltage. It's charged to a large positive voltage. And the other plate, labeled negative, is left grounded, so it's got a voltage of 0. If the metal plates are very large, and by very large, Petra, I don't mean like this big, I mean on the microscopic level, like even 3 or 4 inches, like 5 or 10 centimeters, does the trick just fine. Then it turns out the voltage varies directly with the distance from the plates. So what? Far easier than you realize. Let's imagine that we have the plates separated by 5 millimeters and charged to 500 volts. What that means is as you travel from the bottom to the top, every time you travel 1 millimeter, you've gone through a change in voltage of 100 volts. Because 5 millimeters and 500 volts. In other words, there's 1 millimeter, there's 2 millimeters, 3 millimeters, 4 millimeters. It gives us a lovely straight line linear change in voltage. I'm not going to prove that with you, but you can kind of imagine what's really happening is this. Don't write this down, just look up. Let's suppose that I am a little negative charge right here and I'm moving this way. What does that bottom negative row do to me? Attract or repel? What is this bottom negative row doing to this imaginary negative charge? Attracting or repelling? Repelling. But as I get further, what happens to that repulsion force? Gets bigger or smaller or stays the same as I get further away from it? Gets smaller. But look, on the top I have positives. What are those positives doing? Attracting or repelling? Attracting. And as I get closer, what happens to the force of attraction? Gets bigger, smaller, or stays the same? Bigger. What you actually have is a constant force. As this one's getting smaller, because I'm moving away, right in the same proportion, this force of attraction is getting bigger. It gives us a constant force, which is going to be really nice for like work equals force times distance and stuff like that. And it's going to give us a constant electric field and a nice, not a constant voltage, but a nice linear voltage change. In fact, if you were to graph it, you would say at 1 millimeter, you would have traveled through 100 volts. At 2 millimeters, you've traveled through 200 volts. At 3 millimeters, you've traveled through 300, through 400, through 500. In fact, the voltage is lovely. It's linear, not a curve. The change in voltage is linear. In other words, let's suppose I have a parallel plate right here and a parallel plate right here. And let's suppose I have this sitting at 250 volts, and this distance here is 10 centimeters. Oh, heck. Let's make it millimeters to make it more realistic. So this is negative, and that's positive. If I travel, ready? 1 millimeter. What's the voltage right there? Let's do some arithmetic. What's the total voltage between the plates? What did I write here? 250. What's the distance? 10. What's the total distance? 10 millimeters. So how many volts per millimeter? Sorry? Yeah, right here would be 25 volts. If I travel 2 millimeters, I've gone through a total of 50 volts. If I travel 5 millimeters, I've gone through 125 volts. I have a better picture later on, so don't write that down. In fact, let's go to the next page over. So for parallel plates, we find, hey, there's a constant ratio of voltage drop over distance, and not only that, this ratio is the electric field. If you go back to this graph, the slope is volts per millimeter. And that is the electric field. It's actually volts per meter for electric field. My units don't quite match up, but humor me. What I want you to notice, Curtis, is the slope changing or constant? That means the electric field is also constant. It's going to give us a much nicer electric field. The ratio between the voltage and the distance is the electric field. So here is the key. The electric field is uniform, and it's given by voltage difference over plate separation. Say what? Here is our final equation. Electric field is given by voltage and remember I told you that I'm going to use for the capital V's the little wings to distinguish that from velocity. Otherwise, how do you know the difference? My capital and lowercase v's look the same, so I always put wings on my capital V for voltage divided by distance. Now, we already said this. We already said that you could measure electric field as, see it, newtons per coulomb. Turns out you can also measure electric field as volts per meter. This is kind of, remember gravitational field, you can measure it in newtons per kilogram and in meters per second squared. Two different units for electric field as well. Newtons per coulomb, volts per meter. Hugely useful and has a huge impact on technology. Believe it or not, without realizing it, you've just invented television. Example 2 says, find the electric field and direction between the plates. Okay, so for electric field, I now have two equations. I could go, three equations. I could go, don't write this down. Have they told you the force? Have they told you how big the charge that we're moving is? I'm not going to use that. I could go, don't write this down. That would be if I knew, you know what? Those are for point charges. They don't work for parallel plates. My third equation for electric field, write this down, is the change in voltage divided by the distance. What's the change in voltage? What's the voltage on the left-hand plate? 0. 225. What's the voltage on the right-hand plate? What's the change in voltage? 225 volts. Divided by the distance between the plates. What's the distance between the plates? So in meters, please. 0.03. I get, you know what? The electric field is 7,000 500. I could write newtons per coulomb, but you know what? I'm going to write this one as volts per meter. That's also electric field. That's the magnitude. But what else did it say to find? It said find the electric field and the what, Josh? Got you zoning out, I know. It says direction, good comeback. So how do I figure out the direction? I imagine a little tiny positive test charge, and I ask, which way does that positive want to move if it could? Which way does it want to move? Up, down, left, or right? You're right. Why to the right? Because away from the positive towards the negative. Even 0 is better than being towards the positive. So to the right. And again, that tiny positive test charge, Manisha, so small it doesn't have its own electric field to change the answer of 7,500. So it's imaginary. How does the electric field at point X compare with the electric field at point Y? How does the electric field at point X compare with the electric field at point Y? Well, let's find the electric field at point X. Let's go E at point X. Now that's going to be the voltage at point X divided by the distance at point X. What's the voltage at point X? What's the total voltage all the way across? What's the total voltage all the... You guys with me okay? Yeah? Okay. Want you back here. Elijah, 500. What's the total distance across? 5 what? 5 what? Centimeters. So how many volts is 1 centimeter if it's 500 volts and 5 centimeters? Do the arithmetic in your head. How many volts is 1 centimeter? Okay, so I'm going to say this. The voltage at X, you've gone through 200 volts in 2 centimeters. What's the electric field at location X? Do the math. Sorry? Don't think so. I think it's going to be 10,000. Double check me. Do the math. Yes? Okay, so the electric field at location X is 10,000 volts per meter or newtons per coulomb. What about the electric field at location Y? Well, that's going to be the voltage at the change in voltage. I really should say change in voltage and change in voltage, and the displacement to location Y. If you go from the left side all the way to location Y, how many volts are you going through? 500. And what distance have you traveled going from the left side all the way to location Y? 5 centimeters or 0.05. What's the voltage, what's the electric field at location Y? Sorry, what? So the short answer, when this says, how does the electric field at location X and location Y compare? Michael, what would you say? They are the same. And that'll be the case anywhere in there. No matter what distance you give me, if I know the voltage at that distance, and I'll get 10,000. This is the beauty of electric field between parallel plates. Curtis, it gives us a constant electric field, which means the math becomes much nicer. They are the same. And where it says explain, there's my proof. That's why earlier, I'm going to scroll back up here, I said the electric field is uniform. You know what uniform is a fancy word for? Identical everywhere through. And I can find it, Jordan, by dividing. I always just divide the overall voltage by the overall distance. But you know what? If you give me small locations in the middle there, I can do it too. But easiest is overall voltage divided by overall distance. That's the electric field between those plates. You with me so far? Okay. Big deal. Huge deal. Example 4. How does the electric field at point X compare with the field at point Y? In particular, compare A and B. Now, we've already done the plates, part A. What did we say the electric field was anywhere between those plates? More specific, generically, they are the same. Okay? So, situation A, electric field is constant or uniform. What about in situation B? Is the electric field at location X and location Y the same? William kind of gave his head a very, very slight half shake. Did you?
On purpose.
Oh, okay, never mind. Well, how do I find the electric field from a point charge? The electric field from a point charge is that. Right? We're brushing off cobwebs here. I know it's been 2 weeks. So let's look at situation X and situation Y. In fact, let's go like this. Let's call this electric field at X. Now, K is 9 times 10 to the 9th. That's not going to change. Q is the charge that you're moving. That's not going to change. What is changing is the radius. Compare that with the electric field at location Y, which would be that. Would those two answers be the same? No. Between point charges, electric field changes every nanometer. Like every time you move, Ashley, the electric field is changing, which makes for some yucky math. Between plates, the electric field is uniform, is constant between the plates, which means nice math. So I'm going to say A, E is constant, B, electric field is changing. And hey, there's my proof. Right? The top part of each of those fractions is identical, but the bottom number is different depending on where you are. Again, worth repeating, Callum. Between point charges, electric field and force and energy and voltage change as soon as you move. But between parallel plates, the electric field is constant. Voltage is not, but the voltage changes in a nice straight line, linearly, not as a curve, which is why the electric field is constant. A little technical comment I wrote here. We can see why the electric field is constant inside plates and why it varies if we graph voltage. So if you graph voltage, you get a lovely straight line between plates if you're going from positive to 0. You get a curvy, because it's 1 over r, you get a reciprocal graph. Those of you that are in pre-calc 12, we've seen that curvy graph before. Okay? I wrote here, for all the electric concepts so far, force field and energy, I've tried to connect it to gravity. I said the force equation was very similar to the gravitational equation. I said electric field was kind of like gravitational field. I said potential energy was like potential energy cosmically. What's voltage? Well, voltage is how much energy per charge, the same way as gravity potential is how much energy per kilogram. If we restrict our attention close to the Earth, gravity potential is how much mgh per kilogram, the m's cancel. Gravity potential is gh. Voltage is electric potential. It's sort of like height. When I think of voltage, the difference between 3 volts and 6 volts is the difference between you dropping a golf ball on me from 3 meters and you dropping a golf ball on my head from 6 meters. The golf ball coming from 6 meters, the charged particle coming from 6 volts, has way more energy. And it could be kinetic energy, it could be thermal energy, whatever I choose to transfer that energy into. So, underline this. I think of voltage as height. In fact, when we analyze circuits, we're going to treat it exactly like height, next unit. We're going to say, oh, an 8-volt battery, that's like a ski hill that's 8 meters high. What that means is you can kind of think as though parallel plates is a nice smooth ramp going downhill, and point charges are like a curvy steep hill, for what it's worth. Okay. Homework, and I got a couple of videos to show you, I think as well. So, number 1. Number 2 is good. Number 3 is good. Take a look at number 4. What's number 4 asking you to find? Force. Wait a minute. What did number 3 ask you to find? More specific. Okay, so in number 3, you're finding electric field, which is voltage divided by distance. But in number 4, you're finding force. Hey, is there a force equation that has electric field in it? What? I want a force equation that has electric field in it. You gave me an electric field equation that has force in it. Get to F by itself, please. See, now, because I know the electric field between those plates, I can find out how much force it would take to move a charge back and forth between them. In this case, a 1.25 millicoulomb charge, whatever charge you give me. Okay, so number 4. Number 5 is asking me to find how much work. You can use force times distance. Or you can use work is, we did say that the change in potential energy was equal to Q change in voltage. So since you're going through, by the way, look carefully at this. The left side is 255, the right side is 35. What is the change in voltage actually? It's not 255, what is it? 220 volts. That's the voltage I would use, right? You know what? It's a scalar, but we're ignoring the signs here. It really depends on whether the charge you're moving is positive or negative. The change in is kind of I usually like my voltages to be positive. You're going to find next unit, because Ben Franklin named the charges wrong. Next unit, we're just always going to pretend that we're always going from positive to negative so that we can go downhill and keep the math easy, even though that's technically wrong on a physics level. It's much nicer on a everything else level. Okay. 6 is good. 7, I think I'm going to pass. 8, I'm going to pass. Ooh, 9 is nice. I see a collision and I see a change in speed. This is a combination momentum and energy question, which would be great review. You know, I'm going to try 11. And we're going to pause there. Just give me a second here. Cool.